Our last block of speeches today are going to deal with the reclamation phase of mining. And our first talk today, or our first talk to close us out for this last session, is Gene Bosley. He's going to talk about early restoration of fish passage at Stibnite via river diversion, tunnel, and fishway. Gene is a senior engineer for Perpetua Resources. He leads the design work for the tailings storage facility, stream restoration, fish tunnel, and other infrastructure, and assists the permitting team's water modeling, mitigation, and water management efforts. Gene holds a bachelor and master's degrees in civil engineering and is a licensed PE in several states with 25 years of engineering experience, the majority spent in the mining industry. Prior to joining Perpetua, Gene led civil and hydrologic design and modeling studies for tailing storage facilities, water diversions, stream restoration measures, and ponds at mines in the United States and abroad. So please welcome Gene.
Thanks, everyone. First, I'll start off just a little. I mean, our project is well known in Idaho, perhaps not so well known for everyone here. So I'll just go a little bit about the project itself. Here it is located here east of McCall in the Salmon River Mountains, along a tributary to the Salmon River, which is what we'll be talking about the rest of the afternoon here. It's three open pits. It's a brownfield site, of course. It's 3 open pits, 4 to 5 million ounces of gold, 2-3 million ounces of silver, and about 115 million pounds recovered antimony as metal. And that's all in our 43-101 back from 2020. Again, it's a brownfield site. We have a mine plan that addresses a lot of that. The one I'll talk about is going to be the fish passage issue, but a few of these interact with it. So up here is the pit in question. This yellow, all this yellow is past disturbance. The place was mined for the most part, the 30s through the 50s, abandoned mid-50s. Mined again when the heap leach era began in the 70s, and then that took through the 90s till that was once again abandoned. So this is the pit we'll focus on, but it interacts with some of these other ones. So, we have a lot of legacy tailings and spent leach ore further up the watershed that will get pulled out as part of the mine plan. And we have here, this is related to the pit, is Blowout Creek. Up here, I can't see right. Anyway, yeah, up here is the impoundment footprint of a former water dam that was built in 1917 or 20-something. Failed in 65. It was located in a hanging valley, left a heck of a scar. I think it's 400 or 800 feet above the valley bottom below it, and it's all eroding, still is eroding to this day. Runs chocolate milk every spring, just like that. Well, it all gets trapped in that pit lake, which is the topic of the rest of today's talk. So a river runs through it. It's still water. A river runs through ours. Here that pit is in the 1950s. The river is going around this way. The history there is on the right of the slide, where you see that, in 38 was when that pit first needed diversions. It was discovered a little bit before that, actually due to a pipeline blowout, and they found a nice scheelite outcrop at the time. So initially a surface diversion, later on the Bailey Tunnel. And the Bailey Tunnel, I'll note, goes around back here into Sugar Creek, which flows this way. The East Fork continues then off-frame to the left and on down towards the town of Yellow Pine, about 10 miles downstream. So the Bailey Tunnel was how they diverted it in the 1940s through about 55. Place was abandoned again. The river flowed into the pit. What you would expected ensued is a big steep waterfall and head cutting upstream. Again, fish haven't been able to pass it since then, and still can't. That waterfall can't be ascended by really anything. And anything that descends it is in for an unpleasant ride as well, as you'll see in the next slide. And I should note too, the Bailey Tunnel was about 4 by 6, quite a bit smaller than what we propose here. So here is the present day pit. The river comes in here off to the right. It exits over here. There's a delta forming right here. This boulder cascade is 25% or so gradient and maybe 80 feet vertical in the steepest part, and then it's quite steep up here too, but this part is impassable to everything. And then here is a delta forming where all the blowout creek and other sediment, but majority blowout creek sediment from both the initial failure and the ongoing sedimentation, it all lands in here. This pit started, wasn't in the photo you saw before because that was early 40s, but by the time this pit was done, it was 125 feet below present day lake level. It's filled up to where the max depth now is about 35 feet. So eventually, of course, it'll fill all the way. So here's the basic concept here, right? We're starting, this is our first pit. This is our highest grade pit. The river must be diverted anyway. We'll take it around, slightly long way around, but the correct way around. We'll take it East Fork to East Fork instead of East Fork to Sugar Creek like it goes now. That tunnel, 9/10 of a mile. Pretty early on, before I even joined the project, which I've been on since 2013, it was determined that, hey, if we can get fish up this tunnel, this would be a win for everybody. Because this river has 3 listed fish in it. So we have steelhead, Chinook salmon, bull trout, none of which can swim up this. Now there is a large and plentiful population of resident bull trout above it, but none of the large fluvial bull trout can get up that waterfall. So here's the general concept and cutaway of the pit. This is year 5, which is about the end. That pit goes till year 7, but you see we're ore-bound already. We're pretty far down the cone. And this, again, will be temporary. So this is about a 15-year solution. 15-year service life. It's a solution for even less. We will keep it in service a little bit after restoration because we want that option to divert water if something goes wrong with the ultimate restoration plan, which is this. So that pit will be backfilled. It's our first of 3. The third pit, West End pit, has actually the lowest acid. We have no acid anyway. We don't have acid rock drainage, but when the plan came about, that was the thinking, is that if anything would be the highest neutralizing. Turns out it all is. We never had an HCT go acid despite 168 weeks plus. So we don't have acid, but that will be the most neutralizing rock going in there. It's also our third and lowest grade pit. It would be third anyway. That's the source of this backfill. And so this gets backfilled starting yearly year 5 at small scale, really going at 7, and it reaches river level by about year 10. And about year 12, it'll look like this minus anything actually growing yet. Because year 12, we're done with West End Pit entirely. You'll have everything built up these bluffs and the river corridor and everything built. And then we have 2¼ more years of ore processing from stockpiles. So this will be complete before we're gone. This is a concurrent reclamation project here. So, as you probably have guessed by now, this pit has to go around an active pit that's full of faults. This pit passes a whole river. There is no other way around. So it's a run-of-river facility. And we need to get the adults upstream, but there's little point in that if we can't get the juvenile progeny of those adult fish downstream. And again, 3 ESA species. We also have West Slope cutthroat. Everything will work fine for them. It's a less demanding case because they're smaller and they also swim pretty fast. We'll see in a second it's a non-issue for them, but folks do ask. And of course, it's a river with 25 square miles of mountainous watershed that has a habit of burning. We've got to deal with a lot of sediment and episodically a lot of sediment and potentially timber. We can't let that get into a curved tunnel and plug it up. And then last issue, and I won't hit this hard, but obviously these are ESA fish. We'll have a take permit. We don't want to use it if we can help it. So here a little bit on the geotech. No hard questions, please. I'm not a geotech. I'm just a civil water guy. So tunnel profile goes around the pit, right? The lower portal goes through quite a bit of dump, the legacy dump, the old Northwest Bradley dump. Upper end goes through a little bit. So we have soft ground at each end. Then we have hard rock, semi. It's broken. There are faults. Most of it is in the granitics. That's all the blue. But you do have Meadow Creek Fault Zone. And then you have the Hennessy Shear over here. I should also know Meadow Creek Fault Zone is the the key feature, structural feature of the district here, and the key of chief control and mineralization for those of you geos in the room. Anyway, so what we have here too is low overburden. It's right overhead. If you stretch the string, you took a 4% tunnel, right there is your roof. We don't want to do that. The red line's where we landed in the design. We just flattened that lower bit to 1.5%, made the upper bit 4.5%, neither of which challenging for the fish passage. Get under the bad or the worst of the bad ground. We still expect lots of water in that spot. We know these sorts of troughs, these are I think we believe an outwash feature, and we know it's going to catch a lot of water. We know from all our drilling that all the water tends to occur on the hillsides. It occurs at the bedrock interface, as you'd expect. But this is what it gets us to is, it's a heavily reinforced tunnel. While it is a 15-year solution for us, this is a civil tunnel. If you were designing a water tunnel or a subway, you're essentially in the similar reinforcement levels and a similar service life. If we wanted to leave it there 50 years, it would last that. So we got lots of reinforcement options here. They vary according to the ground. Just various combinations of rock bolting and shotcrete and ultimately steel sets in the worst of the worst. And of course, lots and lots of probing and grouting. Water conditions aren't that bad. However, you saw the water table there. It's in rock. The rock is relatively tight. This is not going to be a terribly wet tunnel where we're worried about unmanageable water. It's not going to be that situation at least. Then soft ground, here we are. The Dale family showed us some soft ground work. We'll do similar except metal. So it'll be a spiles pipe canopy type work. But not cut and cover. We'll drive that through the soft ground. So that's it for geotech. On hydrology, here's the annual hydrograph. This is an average hydrograph. The other spikes, those are pit tag. So that's a passive integrated transponder. That's the chip you put in your dog for when it gets lost. Well, they put them in fish to track them. And they've been tracking Chinook and steelhead for a long time in this basin. We now also track bull trout. We have done a study because bull trout live resident in that pit lake of ours. We've studied those bull trout, and we've got pit signals on them, and some of them went way down the South Fork. So we've got returning bull trout. We have a pretty good idea of when everything shows up. And we need to figure that out because we have to figure out what is our fish passage time from which we calculate the hydrologic parameter, the flow rates to which we design the fishway. And where that got us is, initially we thought, well, gosh, how are we ever going to do a run of the river? And how are we going to make it work for all the fish? We had to focus on, or we thought, well, we'll focus on the late arrivals because the early arrivals can hold. Late arrivals ready to spawn have to get up. Turns out it proved unnecessary. This thing outperformed our expectations. But that was what we were going for here in looking at all this. But where this did take us is we'd have site-specific fish arrival timing based on the regional data, but also based on the local pit tag data for this spot. And that takes us to a cookbook. Now it becomes a cookbook approach where you have your NMFS design criteria as your 5th to 95th percentile from the last 25-year record in the window for the fish and life stage you're trying to look at. And so that's, again, that becomes cookbook calculations, but a necessary step. And we have updated, this is an older figure, but we just did update this and took another look. We had several more years of data. We're now at about 40 years of data, actually. We only use the last 25 because that's the cookbook, but we've got a good 40 years of river data from the gauge slightly upstream of this. So we are blessed in that way. Not all sites are going to have that much flow data. So what did we do after that or in concert with that? Well, we did identify a few examples, and this is all public record. It's the memo's out there. Fish will get up tunnels. They'll get up dark tunnels. They'll get up lit tunnels. They'll get up tunnels that weren't designed for fish in some cases, especially salmon. They're pretty determined, as you can see there going across the road in Washington. And then, of course, we did screen a lot of things, on all your typical engineering criteria. And we looked at everything, including the whoosh system. Those of you who've seen the salmon cannon on Colbert, we did look at it. We looked at a lot. Where it landed, though, was really a really boring and conventional answer was a concrete weir system. And specifically, well, we can do things with either way, right? You could put you could hoe ram a channel in the floor of a tunnel with some detrimental effects on geotechnics, especially now that the tunnel conditions are, based on the rock mass characterization we did for this, as bad as they are in some spots. That will not play well with a steel set, having different length legs. So that, not such a great geotech problem, it's also a terrible hydraulic problem. If the floodplain is the access way, the fishway is here, you can't really control the flow in the fishway very well at all. It turns out the fishway flows get very high for the high range of passage flows. This solution, where you have a control weir at the top, have a partition wall, and the fishway elevated relative to the access, you can send flood flows down this way, or any high flow down this way. Almost all of the high flows go this way, and you can keep all the low flows in the fishway. And that turns out to be the killer app here for controlling velocity and flow down that fishway. And here's how we know it, right? So did quite a bit of CFD, computational fluid dynamics modeling, 3D CFD. That was McMillan. It was then McMillan Jacobs, who was these guys. They did, I thought, a great job. I've done some CFD myself, but we were stuck with 2D back then, and it took days to run. So these guys have brought us into the 21st century with their modeling here. And where we look at it, of course, it's, a few key locations, first fishway weir, and then within the fishway, down in the tunnel. And then, really all of this is one system, is this or there. The flow can go either way. So this is all analyzed. This is one model domain you're looking at here. And we look at that at both the slopes of the tunnel. We look at that all the way up to the 500-year. We can't have this thing overflow into the pit. So 500-year flow minimum. Turns out has a lot more capacity than that. And we look at the full flow range for all the species of interest, which is a wide one. It's up to 239 CFS on the high end of steelhead, because they come in the spring when the hydrograph's on its way up. And here's what we got is we analyze here. We don't look at here. These are boundary effects. This is the section that's really representative. Take note, too, of these velocities. And this is what we need to achieve. Bull trout, despite eating salmon, are actually a slow swimmer. It's 6.6 feet per second. And here's what we got. And this is at a high flow. This is the high end of bull trout and Chinook salmon flows, 6.5 feet per second. Just good enough for bull trout by a little, not even a challenge. It's under the sustained speed of the faster fish. Here's some sections through that same thing, just showing lots of eddies, lots of low velocities. You've got that little jet, it's all over, but the jet decays and you have an eddy. Every one of these pools is a resting pool. So every 22 feet in the steep section, resting pool for the fish. How we doing on time? That's been up a while. Okay, all right, we're doing all right. Here's some more of it, same thing. This is just a pretty picture of this thing at a very high flood flow. So a lot of water goes down that access way, and it's moving fast. That'll have some effects we'll hit in a second. That's just data. Here's what it ends up with as far as physical features here. This is the configuration of this thing, and I'll work it. This is from the viewpoint of an adult swimming upstream. So down at the bottom, blue arrows are flows. Blue arrows are flow direction. So fish will come up. There's a little approach channel off frame. There's a barrier here. This is to keep anything from trying to ascend that access way, because all they would do is try and fall back and exhaust themselves, because it's not ascendable. It flows very fast. It's a smooth, shallow flow that you don't want fish going up. Then you have a few, the first weir, the big resting pool below it. Again, superfluous. Every pool is a resting pool here. We didn't know that when we laid out the initial one. And then up the fishway. Not shown because it's too small to show. This is also a trap and haul facility. There will be a crowder. Should the fish decide they don't want to use this, which I think it's little challenge to their swimming abilities, but you never know behaviorally, we can trap and haul here, and that's 99 miles better than the present trap and haul. Like, it would be a mile or two upstream if we had to get them around this that way. We don't think we'll ever need to, but it's built in to do so. The other thing is here with this barrier, there's a pool behind it too. Any juveniles that do come down the access way, likely to be disoriented, likely to end up food. We have 3 listed species. Thing is, they like to eat each other. The bull trout, the large ones, and the cutthroats will eat the juvenile salmon. And while that is going to happen as they run the gauntlet downstream, we certainly don't want to facilitate it here. And you see that other fishways struggle with that as well. Here's inside, simple enough. This is an arched tunnel, 15 by 15 feet. So this is almost quadruple the cross-sectional area of the old Bailey Tunnel. The 500-year flood comes to spring line. There's not a flood capacity concern here. And again, it's just a partition wall with a series of concrete weirs. That partition wall is going to get slip formed like a Jersey wall inside of a highway tunnel. Here's the other end. So coming out, you've got another big resting orientation pool. There will be screened pump intakes here for a water withdrawal. Here's a debris screen, size wide enough for a Chinook, but not wide enough for a lodgepole. Here's a big flat reach to drop out debris, and here's a big sump to drop out the biggest of the big bed loads to try to keep us from having to chase it all through this reach. Big stuff will drop out here, and anything bigger than pea gravel will drop out here. We will have to vac out a couple of the first bays of the weirs due to sand and pea gravel size material, we think. So that's it in a nutshell, but here's what we find when we get up there. Not, again, another hour presentation is what the restoration plan is elsewhere. Well, it's about 12, this number's wrong, it's 2.3, but this is about right, 12 miles of restored stream, another 2.3 of non-perennial, which aren't fish habitat, of course, for the most part, seasonally maybe. But here's that barrier. There will, unfortunately, be a new one at the tailings facility because it's a 400-foot high dam. We decided we wanted to do that rather than put the tow down here and consume all this good valley bottom habitat. So new barrier here, old barrier here, another old barrier right there that also gets removed. It's just an old culvert, box culvert. Now, all this, mine's never touching this. This is the East Fork. That's all cold. The only human impacts are a few roads, a few exploration trenches, and forest fires. And forest fires were not so much human, it was lightning caused in most cases. So all that access gets open. That's about 20 stream miles of open access because of this tunnel. And again, it's project outset. This is the beginning of the project. This is second year of construction of a 3-year construction phase, and we'll activate it really the year we start mining. So, and that's about the end of it, and that's the summary, but I just said it, so I don't need to say it again, I suppose. We got 5 minutes and Q&A.
Great. Thanks, Gene.
And I'll return to slides as needed if you like.
Any questions for Gene?
Given the ESA issues with the fish, did you have to get a biological opinion from the Fish and Wildlife Service?
Yes, we've got, the BO is pending. I think I don't know the status right now. I think the BA has gone in. The BO is pending, I think is where we're at. But yes, absolutely. And we've had review, and we have another document. This design's all out, but there's also a 160-some page operations plan for that tunnel. All of that has gone to them. They've had it for a couple years now. And their engineers have reviewed the fishway design. So their engineer out in Portland or Seattle somewhere has reviewed all that. And they seem all right with that part. Their concern is always going to be fish handling and take and issues elsewhere. I think they'll have something to say about the detailed design of the tunnel, but I don't think that's going to be the big hang up on ESA. It's going to be talking about all the other things of restore this, when, and what water temperature, where. That it's more to it than the tunnel that's going to go into that biop.
All right. So looks like no more questions, Gene. Thank you.
All right.
Appreciate it.